morning, everyone, and thank you for coming. Today we have a new lecturer, and it is my pleasure to let you know that Professor Samir Mathur from the Ohio State University of United States has kindly agreed to visit us and to give a series of lectures at the school. Mathur Samir research interest is focused on string theory, black holes, and ADS-CVT correspondence and cosmology. He's a professor at the Department of Physics of Ohio State University at the present, and he was a faculty member at MIT and held positions at Harvard University and Tata Institute for Fundamental Research. He's very well known for developing the Fuzzball conjecture as a resolution of the black hole information paradox, one of the fascinating topics of modern science. And he will give a series of lectures, these fascinating topics, information paradox, and namely resolution of this paradox in the context of Fuzzball paradigm. Please join me to welcome warmly Professor Samir Mathur.
Thank you. Okay, thank you very much for the invitation to come to this wonderful place. So I would like to talk in these lectures about what I have been thinking about in regard to black holes for the past many years. And here is an outline of what I hope to do. First, I will tell you what is the black hole information paradox. That's the puzzle which was discovered by Stephen Hawking in 1975. Since then, the puzzle has actually only become stronger. You can actually now make it, his initial difficulty which he raised, you can now make it into a rigorously defined problem, into a kind of theorem. For a long time, people were not taking this paradox too seriously. You would think that people in string theory should worry more about the information paradox, because what Hawking had argued was that you cannot have general relativity and quantum mechanics hold at the same time. That's obviously a big problem, because both general relativity and quantum mechanics are two of the fundamental pillars of modern science, and the information paradox says that general relativity will make black holes, and once you have a black hole, you will have a breakdown of quantum mechanics. So that is such a serious problem, you would think that string theorists would be really worried, because they are really trying to make a quantum theory of gravity. The reason people didn't worry about this too much while developing string theory was that there was a belief at the back of many people's mind that Hawking's argument was perhaps a rough argument, and in some way that we don't really know, maybe the information is actually somehow delicately encoded in the radiation from the black hole. Okay? We now know that is not the case. There is no kind of subtle encoding that you can actually do to the Hawking radiation, and in fact, if you can actually make a black hole the way you see in classical mechanics, you will lose quantum theory. Okay? So in fact, we are looking for a solution which is really going to have to be rather radical, and the small correction theorem tells you that you cannot delicately encode information. You actually, as I'll explain, explain the problem's technical foundation in terms of something called entanglement, and the entanglement of the hole with the radiation keeps rising, and if you do small corrections, it still keeps rising. So somehow this delicate encoding business, I will explain, really cannot work, so you completely need to change the picture of a black hole. But what should be the answer in string theory? I'm going to argue that what happens in string theory is that when you try to make a black hole, after all, you have to make a black hole using the objects which you have in the theory, which are strings and branes and objects like that. So you have definite objects, you have definite rules in string theory about how they combine and how they behave. So you have to make a bound state of strings and branes. So what I'm going to argue is that every time we have actually tried to make a bound state of strings and branes, maybe 1,000 strings and 1,000 branes, and say, okay, maybe we make a black hole. But when you do that, naively people thought the size of the bound state would be something like Planck length or string length, something small, and then if you have a lot of brains in here, the horizon would be big. You could make a 3-kilometer horizon like that for a solar mass black hole. And so what you're doing with quantum gravity here, in that case, certainly wouldn't matter. And you are back to the classical picture, and then also all the information puzzles. What we seem to find in string theory, though, is that as you put more and more brains together to try to make a bigger black hole, the size of the bound state actually keeps rising with the number of brains. So in fact, you can never actually make a bound state. It doesn't matter how many brains you take. You can't make a bound state which is compact enough to actually make a black hole. The size of the bound state always comes out to be of the order of the horizon scale. So somehow the solution in string theory in the end then would be claimed to be very simple. You just can't make what you would classically call a black hole, because the stuff just never goes in. When you try to add energy to brains, like more and more brains to make a big black hole, the brain just swell up, and so you never actually go inside the horizon. And then of course you have no puzzle. You basically get something like a stringy star, and then physics is normal from here onwards. What I've been working on in the last few years, I'll try to capture in the last talk. All this is actually relevant to cosmology, because we have somewhat different sounding, but again very deep puzzles in cosmology. For example, we have the issue of the cosmological constant, but also we can ask things like, there's a cosmological horizon. Is that at all like the black hole horizon? If in black holes the horizon doesn't form, what about the cosmological horizon? So there are many, many deep questions in cosmology to which we can actually even get answers by looking at observations in the sky, and some very interesting connections emerge between the black hole puzzle and the cosmological puzzle, and I'll talk a little bit about that maybe in the last lecture. Okay, so let me get started. And we'll begin with very simple things, but before I begin, let me say that I would actually like to get your questions during the talk. Black holes is a very crazy field. In most fields of physics, you sit down and you calculate. In black holes, you basically argue, because after all, we are looking for the most fundamental issues in quantum gravity, and so most of the work is actually done by arguing just about the basic principles. So I'll talk in very, very simple terms here, and I'd also like you to stop me every time you have a question, or you think something can be done not like this, but like this. Then let's have a discussion, because discussing these issues is somehow the best way to understand the puzzles that we are having. So please feel free to just stop me and ask questions at any stage. Okay, so the whole trouble with black holes is actually very, very simple to understand, and it's a very robust problem, as you can see just from the place where we start. And it all comes from something that you know very well, which is that gravity is an attractive force. So if I drop this, it falls down, and that's all that you need to know. Gravity is attractive. From there, we'll see that you can't get out of the information paradox. So let's just begin with simple Newtonian mechanics. Gravity is an attractive force. So if I take a mass capital M here, and I put a test mass little m over here at some distance r, then this mass, we give it a potential energy, and the potential energy, as you know, is this formula, minus g, big mass, little mass over r. The attractive nature of gravity is encoded in this negative sign. Okay, so that's why gravity is attractive. Now if I just had this mass by itself far away from this mass, it has an intrinsic energy, which Einstein told us is mc square. Okay, and that's obviously positive. But now when I place this mass close to the big mass, then what energy should we attribute to this? Let's just go with our simple Newtonian intuition, and then the energy of this mass would be its intrinsic energy mc square, and then you would add the potential energy. We're obviously being very rough here. Once I have special relativity and all this, really we should do general relativity, and we will later on. But we are just going through the hand-waving first pass at the puzzle. So the total energy of this guy is its intrinsic energy mc square, but because sitting in a potential, then this is the potential part. Okay, so I just copied that thing again on this slide. But now you see, because there's a minus sign here, as we keep making r smaller and smaller, the negative term actually starts growing. And you can see when r reaches this value, the total energy of this guy actually becomes 0. Okay? And if I make r even smaller, then the total energy of this guy becomes negative. So this is, I've just drawn a circle here at this radius gm by c square. You can see this can be quite a big radius, because as I keep increasing m, this will be a big radius. But this is the critical radius. Later we'll call this the horizon of the black hole. But anything placed inside here, you can see has a negative total energy just for this simple reason. Now you can see, if you have agreed to everything so far, then you already have a deep problem. Because if I just have this mass by itself, capital M, then its energy is capital M times c square. Normally when you add one more particle to the system, let's say this mass little m, you would think the energy goes up. Like if you have more stuff, maybe it has more energy. But now I added something, but the total energy went down. This guy had an energy mc square which was positive, but because the potential energy is negative, the total energy actually went down. You added something, but the total energy went down. That looks funny, and then you can keep doing this, right? You can keep adding lots of particles in there, and then you can keep making the total mass smaller and smaller. Okay, so as long as I can keep doing this, I can also make the total mass 0. Okay, just keep cancelling it. And where did all this cancellation come from? Each object itself had a positive energy, mc square, but because when you bring them closer, the potential energy is a negative number. If you put them sufficiently close, the total positive energies can cancel the negative potential energies, and the total energy can be 0. So you see, I can make an object of 0 mass. I can actually make infinitely many objects of 0 mass, right? Because I can start with a central mass which is as big as I want, and I can dial it down to 0 by putting lots of little masses, and now here I have made infinitely many possible objects which all have 0 mass. In some sense, this is the essence of the black hole information paradox. Such objects, should they exist? If there were infinitely many 0 mass objects around us, we should have seen them. In fact, they would create some difficulty for physics. Every time you have an interaction, you end up producing particles. Which particles do you produce? Well, the low energy particles are produced in more numbers, right? Well, if there are infinitely many objects with 0 mass, you probably produce them in any collision, and all of physics would become completely senseless. So obviously we don't see these guys around, but what's wrong with this logic? Okay, so of course so far we have just been talking very roughly. We use special relativity to use mc square, and then we use Newtonian gravity to use minus g mm over r, and you know that when we include relativity and gravity together, the true theory should really be general relativity. Okay, so let's just look at a pictorial view of general relativity. Whole idea of general relativity was that if you have a mass somewhere, it curves the space-time. So here's my cartoon of general relativity. You have your light cones there. You can think of time as going up and space as going this way, and so if there's no heavy mass anywhere, space is flat and particles move on straight line geodesics. But if you have some heavy mass here, then of course space-time is curved. The light cones also sort of bend inwards, and now something, if this was the sun, the Earth would now follow a geodesic which is curved, and you know this is time, so the Earth is sort of going around in orbits. Just a cartoon picture of general relativity, which you know very well. But the reason I drew this cartoon is that we want to understand the picture of the black hole. So again, you can think of time in some sense as going up. This is just a cartoon picture. This is the radial coordinate, and these are the angular directions. So if you have a star which is start burning and is collapsing, this is the horizon radius. It starts out bigger than the horizon radius, and far away the light cones point up as they would in normal situations, and here they're pointing slightly inwards, and as the star collapses, they point even more inwards. But once the star becomes this big, you see the light cones have actually tilted in such a way that from here you can't even get out. You can stay at best at the horizon or go in, but as long as you travel at less than the speed of light, you can't actually go out. So when you reach the situation, you say a horizon has formed, and the star itself now has no choice but to keep collapsing, because every point in the star now has to just keep moving inwards. So now it can't stop itself from collapsing, and once you're inside the horizon, in fact the light cone points purely inwards, so you have to go in. You can go in fast or go in slow, but you can't even stand at one place, and so you keep getting smaller and smaller, and the whole thing collapses to a point. So why is this important? This is important because in the previous slide when I said, well, here is my mass capital M, and near there I'll put a mass little m, and therefore I will get negative potential energy. I did need that mass capital M to be point-like or small. Why small? Because I want to come close enough to it. Okay? Now, if my object was always big, like why can't I do this with the Earth? I can bring something closer and closer to the Earth, but once I reach the surface of the Earth, I get some minus gmm over r potential. But if I go further in to make it and make the r even smaller, the formula changes, right? It's not minus gmm over r, because now I can only see the mass which is inside a given sphere and not the entire mass of the Earth. So I don't actually want to reach the surface of the object. If the object is very compact, then you can play the magic I was talking about on the last slide. But now you can see, if you have, once a star collapses inside Schwarzschild radius, it has to keep going to this critical radius, and then it's going to keep going to zero size, and once it goes to zero size, all this region has to be blanked out. Nothing can be here, because as long as everything moves slower than the speed of light, it's going to keep getting flushed out from here. This region will all become the vacuum just because of the structure of the light cones, and everything really goes to a point. And so now you see, I am actually getting the kind of region with now general relativity included, which will play exactly the kind of magic we were talking about. Any particle here, we'll see, has net negative energy. Okay, so the black hole, that's why we need the black hole for that simple story we started. We want to know whether we can make things compact enough to be a point, and look here, they are becoming compact enough. Yes?
In the case of energy, we should say that in which reference frame are they speaking? For example, we are measuring the energy from the point of view of an observer which is sitting in the infinity, or the observer.
Very good question. I meant the observer at infinity. So far, of course, it hasn't come in the discussion because we have been so rough. We were just Newtonian, we were not drawing any space-time diagrams. But later when we draw the black hole properly, we'll see it is indeed the energy at infinity. Right? And so in technical terms, just to take a little diversion, energy at infinity is measured by taking the 4 momentum of any particle and taking the dot product of that with the killing vector del by del t. And what ends up happening is the del by del t actually vanishes at the horizon. The norm of that vanishes, and inside the del by del t actually becomes space-like. And once del by del t is space-like, if you take a 4 momentum of a normal particle and take a dot product with that, it can have either sign. And so it can in particular have a negative sign. So that's the technical meaning of saying if you put a particle inside, it can have negative energy as seen from infinity. Okay, so exactly. So everything I said was actually true, though very imprecise because we were being Newtonian, but in the end, all these statements will be exactly true, even with general relativity.
So you assume existent ergosphere as well?
Ergosphere. Okay, so at the moment, that doesn't matter. This was a non-rotating thing, but as long as there's a horizon where the light cones actually go inwards, you're going to have this problem. You can actually have an ergosphere for a neutron star, right? Just a rotating star, where you don't actually have causal trapping. Then there is no problem. I mean, you can have an ergosphere where you can get a particle which has net negative energy as seen from infinity. That is true. But you won't actually get all the way to the information paradox because we haven't yet come to the information paradox part. So an ergosphere will still have particle with negative energy, but will not have the information paradox. But when the ergosphere has inside an actual horizon from which you can't escape, then we'll have the real problem. Okay, so then you might wonder, if black holes are going to give us so much trouble, maybe there aren't any black holes. Maybe when you make a proper theory of quantum gravity, somehow maybe black holes don't form. Why didn't people think about that? After all, nobody had actually gone in and seen what happens to the collapse of a star. But it turns out it is very hard to stop black holes from forming. And for that we can see the math very easily. The critical radius we had already found from Newtonian estimates was gm over c square. If you do the whole thing properly with general relativity, you only get an extra factor of 2. So let's use that number from now on. And suppose the mass density is rho of a ball of dust, then the total mass in radius r will be given by this expression. And so when do you actually get a black hole to form? If you put this value of m, so if you take a density rho in a radius r, you put it in here, the equation you are getting is r equals this. That's the condition for getting a black hole to form, and that gives you a density equal to this. So if you take r very big, so you take a dust ball, this is all a constant, you take a dust ball with a radius r, with a radius r and make r very big, then you need to have the dust ball with a radius, with a density which is very small, and then that will just make a black hole. So you can even take particles of dust, let's say 1 gram particle, you put one here, and then another 1 gram particle 1 meter away, another 1 gram particle 1 meter away, and make a cubical lattice. Now this is so low density, you might think no new effects can come in. When 2 dust particles of 1 gram or 1 meter apart, well, you don't think anything new can happen. But if you take this kind of lattice and make it big enough, several light years big, you will find that you meet this criteria. That stuff is already inside this light cone, it has to just keep. It's in here, and then as we have seen from the light cones with very low density but sufficiently big radius, the light cones outside that have turned inwards, so the whole thing has to keep collapsing. So how do you ever stop a black hole from forming? Okay, so now we are actually locked into our difficulties. If you take a low density stuff where no new physics is supposed to happen, it already tilts the light cone and will squeeze itself to a point. If it squeezes to a point, then in all this region you get effectively, if you put a particle, net negative energy. You can keep putting particles there and make something of zero mass. We'll see the puzzle in more details in a minute. And once you can start cancelling the mass down by using the negative gravitational PE, well then you can run into lots of puzzles. So this is the essence of why black holes are going to give us so much trouble. Okay, so then as we said, repeating the whole thing with general relativity properly just gives an extra factor of 2, and that's the critical radius. We'll call that the horizon, and if you put something in here, it will have net negative energy. This is the essence of everything we take away from what I said in the last 10 minutes. Okay. So now you'll of course know that when you hear people talking about black holes and the information paradox, there are so many pictures, so many solutions, so many theories that people have posed, and it looks like a complete mess. But you can become experts on black holes very easily. we'll just give ourselves a set of questions. So if anybody comes to you saying, this is my way of solving the black hole puzzle, you should ask him these questions and you'll be a complete expert. Okay, so what questions will you ask him? The first thing you will say is, in your model, do you have a region where the energy is negative? That's what we said. In here, the mc square minus gmm over r was negative. That was the whole root of the problem. So have they somehow removed a region where they have negative energy? Because if you have that region, you have the problem. Okay, in that model, suppose they don't have such a region, then that means they didn't have this kind of horizon. Maybe they prevented this guy from ever collapsing to a point, and then of course there wouldn't be a problem. And then you have to ask them, if not, then how did you stop the horizon from forming? Because we've already seen a very low density object, if there's enough of it, the light cones will turn around. Okay, so at low density nobody could stop it, so what magic has he used to stop the horizon from forming? Okay, does that look good? Any questions on this so far? So the problem is so simple and so basic, that's why it's so robust, and that's why there was just no easy way to solve this for a good 40 years. Okay, so now let's go and see what Hawking did with this. So we again go back to this picture. If you put a particle in there, it has net negative energy, but how would you actually go and place a particle there? I mean, can you pick a particle, like reach in and put your hand in the black hole and put it there? Now nobody has actually done that, so you might think that all this is good theoretically, but maybe there is some reason we actually can't put the particle there. But actually what Hawking found was that quantum mechanics will automatically do that for you. Okay? And so as you know, even in this room where there's no black hole, if we have just flat space, there are always fluctuations going on. So out of the vacuum, you could have an electron-positron pair fluctuating up for a while, and then it annihilates back again and goes back to the vacuum. That's the electron and the positron, and after a time they go back to the vacuum. Of course, the vacuum has zero energy, and this thing costs energy, let's say mc square plus mc square, but that extra energy delta E, because of quantum mechanics, can always be borrowed for a time delta t, as long as delta E times delta t is less than or equal to h bar. It's just quantum fluctuations, yes?
I realize I should have asked a question when you were asking the questions. Could we go back to that slide?
Previous slide?
No, the one before. Yes. So, this so far is about particles moving inside the horizon.
Yes.
But the question of whether the information moves inside the horizon is a different question.
Yes, we haven't come to the information yet.
Good.
Right. Right now we're just seeing what a horizon does, and then we'll see where the information story is.
Okay.
Yeah, we haven't done that.
Good to be clear about.
Yeah, but a little bit we have actually already said about information, if you like. In a way, we actually had it on this picture, because this is actually, in a sense, the information puzzle here itself. If I take a mass capital M, which could be as big as I want, and I dial it down to 0 by putting all these little m's in here, the reason I gave these different colors is that some could be electrons, some could be positrons. So there are infinitely many ways of making zero mass objects. And so you could say, I have my total energy is 0, but or maybe Planck energy or something where it saturates when you do the story, but total energy is bounded at somewhere between 0 and Planck energy, but the degeneracy there is infinite. And that is the one way of talking about the infinite amount of information. So in the end, this will be, in a sense, we have already seen the information puzzle in one guise here. Okay, so what did Hawking say? So as we said, we can always borrow some energy delta E for a time delta t, as long as we don't borrow it for too long. Delta E times delta t should be less than or order h bar. That's just vacuum fluctuations, and they are happening everywhere in this room. They just don't last very long. But you can measure these in the lab. Okay, the effects of these can be measured by particle physics processes. But now if you have the same fluctuation near a horizon, then it's interesting. One particle could be just inside the horizon, and one particle could be just outside. Now the guy inside can have net negative energy, as we said. mc squared minus the potential energy becomes negative. The one just outside will have positive energy. And the total energy now can be 0. And in that case, if you plug it in this formula, you see that delta t can be infinite. So if you make a fluctuation where the total energy is 0, because one guy was negative, one guy was positive, and you can see it's the attractive energy which is helping me here. The fact that gravity is attractive gave me the negative sign of PE. Then in fact this is an on-shell process. There was another, if this state by itself had energy m, adding this particular pair didn't change the energy. Net energy was 0. And whenever you have another state with the same energy, you can of course go to that state, and you don't have to come back. It's an on-shell process. Your wave function of this state will just spread over, also including this state after a while. So it will spread over this state. So you create this particle pair, and now this guy can just stay there, doesn't have to fluctuate back to 0, and the guy which is outside can now drift off, and that's the radiation from the black hole. That's what's called Hawking radiation. So where's the energy of this radiation coming from? If you're sitting at infinity, you will collect this particle. It will be a normal particle, mass mc square, so you've got some energy. Where did the energy come from? Well, this object which is left behind now has less energy because this m was there, and this was little mc square, but the gravitational PE was negative. The total thing now has less energy than just capital M, so this thing lost energy and the particle came out, and that's the process of Hawking radiation. So one particle is emitted, it leaves this partner behind. The whole black hole I've drawn a little smaller now because the total energy of this object now is a little less. So the radius 2g m by c square is a little less. You can see this is a little smaller, but the process can repeat and you can just keep going, and after all after some time the energy of the whole all ends up in the radiation, and you have all these particles collected, so energy is conserved. Okay, so this is the process of Hawking radiation, and this is what Hawking found in 1974. Yes?
So what is the difference between this process and the process of throwing something in the black hole? When you throw something in the black hole, the radius gets bigger, but when this happens, the radius gets smaller.
Okay, very good question. So I was actually, I said that how do you reach in and place a particle in the black hole, right? So why was I making such a fuss about that? Then I said Hawking said quantum mechanically you can automatically create them, they come inside. But why did you need Hawking there? That's what you're asking. If I want to put something inside a black hole, I don't have to put my hand in there, I can just throw something, it will go in, right? But if I just throw something, when it goes in, it doesn't actually have negative energy. And what is the reason? As something falls along a geodesic as it goes in, its energy is conserved. So if at infinity its energy was positive, just mc square, as it falls in, yes, the PE becomes more negative because it's going in, but the kinetic energy is increasing. So you have the intrinsic energy mc square, you have the negative PE, we already talked about these two things, but you also have kinetic energy. And the total, if you add all three, will be positive because energy is conserved. So that doesn't really help me. So if you throw a particle from outside, when it gets inside the horizon, as we said, inside the horizon you can have energy either positive or negative. If you throw it that way, then the energy there will be positive. Okay? So in fact, it's not easy to get negative energy. If you place a particle there with no velocity, if you like, then it will actually have negative energy. And so if I go back to this picture I had before, we'll come back to all these things in due course. If you look at this light cone, a particle which you throw in is going very fast. That's the guy going this way. Okay? Those guys have positive energy. The guys going this way, which are trying to go out, but of course they can't, right? They can't even stay in one place. They still have to keep going in, but they're trying to go out on the outward side. They have net negative energy. So that's the point. So how do you put a particle there with net negative energy? You can't throw it in. And what Hawking showed was, well, by quantum mechanical fluctuation, when they are created like this, then in fact those particles can have net negative energy because they appear there with no velocity. That's why the whole Hawking thing is so important, and you can't actually just put the particles there. That's a very relevant question. Is that good? Are there more questions here? So where were we? Yeah, we got the Hawking radiation, and so the black hole is evaporating away. You can see it's also very robust. We just use the fact that gravity is attractive, and we just keep going, just using even Newtonian estimate gm over c square minus gmm over r for the and mc square for the energy, and then you can just say the black hole has to evaporate. Okay, what's the problem with this? Well, let's say where the process will end. Hawking in fact assumes since the black hole is evaporating, it will just disappear, so in the end you'll be left with a vacuum over there, and you'll have all the radiation here. That looks like a beautiful process. But of course somebody could argue that once this object which is left behind gets down to Planck size, then quantum gravity effects will take over. You don't really know what is happening, so possibly it could stop there, and when it stops there, what is left behind, we call it a remnant. Okay, that's just a technical word. So these are two possibilities, but in fact, either of these two possibilities will give us problems. So now let's see what the problems are. Okay? But already at this stage, since we are trying to become black hole experts, let's see what questions you should ask somebody if he comes to you with a theory. The first question is, if you have a horizon, then are you going to stop the process of Hawking evaporation? So if you have a horizon inside which you can have negative energy modes, then the vacuum fluctuations are automatic. So you will get all these particle pairs coming out and the hole will be reducing. That's the Hawking process. If somebody says, no, in my theory, the black hole does not radiate and so I will have no information problem, you have to ask him how. Because near the horizon, the space is smooth, just like this room. If fluctuations happen in this room, they'll happen there. So how does he not have his Hawking evaporation? And then somebody says, is the evaporation not stopped or altered in some way, then does the black hole evaporate away completely? That's what Hawking said, it goes away completely, or are you going to be left with a Planck size remnant? So all different theories which people propose for the black hole will try to say, no, this doesn't happen, or this doesn't happen, or this doesn't happen. So of course you have to ask him which of these things is true. Okay, so now let's see what's the problem with Hawking evaporation. When Hawking found this in 1974, he was just actually very happy. Okay, but his happiness lasted for 1 year, because in 1975 he found that there is a serious problem with this Hawking evaporation. So what did he find just in the next year? And the crucial issue has to do with entanglement. So we said that the electron and positron can be created out of the vacuum like this. I drew the electron on the left and the positron on the right, but of course it could be the other way around, right? You could have the positron on the left and the electron on the right. So in fact, you'll get vacuum fluctuations both with the electron inside and with the positron inside. And because it's a quantum process, you will of course typically get a linear superposition. So you have a linear superposition of these two quantum possibilities. And now you see the particle which has come out, you don't actually know if it's an electron or a positron. It has what's called an entangled state. So an entangled state is a state which is very common in quantum mechanics, like two spins can be entangled when you have a singlet state for two electrons. And so there's nothing wrong with having entangled states. If you have two electrons, they could be in a state where this guy spin up times down, minus down times up. And then if I ask, you look at one electron and say, what's the state of this guy? Well, that's not a well-defined question. This guy's state is up. If the other guy is down, it's down. If the other guy is up, it's the conditional statement. If I just look at one electron and say, what's the state? Well, there's no good answer to that. The overall system has a state. So again, if I ask you the particle which came out as an electron or positron, that's not a good question. It's a positron if the guy inside was an electron. It's an electron if the guy inside was a positron. And so what you can see is the radiation state, the guys which come out, are entangled with the state of what is left behind. Okay. So the entanglement can come from many sources. As I said, I was using electrons and positrons, so you can see they're entangled. They can, which guy comes out, you could talk about that. But you could say, well, I don't want to radiate electrons. Maybe my theory has no electrons. It only radiates neutral particles. But it could be spins. If the spin up is in the outside particle, spin down would be the inside particle. It would come out typically in singlet. It could be spin. Then you can say, okay, I don't even have spin in my particle. Let's take a chargeless, spinless particle and worry about the radiation. But that's actually the most basic kind of entanglement. And that's the entanglement Hawking actually considered. Because in every region of this room, there's a field theory quantum mode. If this mode is in the unoccupied state 0, there's no particle here. If it's in the occupied mode 1, then there's one particle here. If I put occupation number 2 for that mode, it's 2 particles. That's how we do quantum field theory. So in fact, because these quantum fluctuations themselves are probabilistic, okay, you might or might not create a pair at a given time. It's all random fluctuations. The actual state will be some number for the unity times having no state here, no particle here, and no particle here. No pair is produced at that time, or one particle here and one particle here, or maybe even 2 particles here and 2 particles here. So in fact, the occupation number of the particles itself is also entangled, right? There's nothing here and nothing here, but if one particle comes here, then one particle comes here. You have to create everything in pairs. Okay? So in fact, if nothing else, the occupation number will be entangled. So in any case, because of these entanglements, or at least the occupation number entangled, the occupation number of the outside mode is heavily entangled with the inside mode. So if you want to write the formal way of writing an entangled state, how do you normally think of an entangled state? If you have 2 different systems, let's call them A and B, a state which is not entangled has the form some psi of A times chi of B. If the whole state has the form psi 1 of A times chi 1 of B, plus psi 2 of A times chi 2 of B, okay, you have 2 terms in the sum, you say the entanglement is 2 units roughly. The numerical number we give to that is log 2. If there are 3 terms in the sum, all with equal weight, psi 1 chi 1 plus psi 2 chi 2 plus psi 3 chi 3, we say the entanglement is log 3. Okay, that's just a way of measuring entanglement. So you can see that this, we'll come to the actual definition of entanglement in more detail later on. You can see the particle radiated is entangled with the particle left behind, and that's going to play a crucial role. Because the entanglement of what is radiated with what is left behind will actually be very large. And that's because the number of particles you radiate is very big. Black holes are heavy objects, so they'll emit lots of particles, and each particle is entangled with what is left behind. So you can see how big the entanglement will be. Let's just go back to the model where we have electrons and positrons. Let's call electron as 0 and positron as 1. If all the guys outside are electrons, then all the particles are positrons, right? But they could be coming out in any sequence, electron, positron, and so on. And the mirror of that would be here. So the total state is this times this, plus this times this, plus this times this. There are 2 to the n terms in the sum. Okay, and so then you would say that the total entanglement is n log 2. You take the log of that just to sort of as a quantitative measurement of what the entanglement is. If there are 2 to the n terms of the sum, the entanglement is n log 2. So if you emit n particles, the entanglement is order n. Okay, so n is very big, so state of this guy is heavily entangled with this. But what's wrong with that? In general, everything in the universe is entangled with everything else. The problem comes because of what happens at the end point of evaporation when the black hole is trying to vanish. Let's go back to what Hawking initially thought. He thought, well, the black hole is evaporating, let go away completely. I have just a vacuum here and only these guys left over here. Well, now you have a problem. If you have an electron, two electrons in a singlet state, you can move them quite far apart. You can keep one on Earth, one on Mars. There's no problem with that. Still, the electron here doesn't have a state of its own. It's up if the other guy is down if that guy is up. But there's no problem. That kind of thing happens all the time in the universe. But the problem comes if the electron which is on Mars somehow not disappears from the universe. That's what has happened now. These things went away. Now, if you look at what is the state of the electron that remains here on Earth, you have a problem. Is it spin up? We don't know. Is the spin down? We don't know. Because spin up was true if the other guy had spin down, but the other guy doesn't exist any longer. So now the guys who are left, actually they can't be described by any quantum state. And this is the crucial discovery of Hawking in 1975, that once a black hole forms and evaporates, what is left behind cannot be assigned any quantum state. It can only be described by what's called a density matrix. You can give a probability. It has 50% probability for being up, 50% probability for being down, but it doesn't actually have a quantum state. Now that's very serious because normally everything has a quantum state. Right? When you started with a star which was going to make the black hole, it had some very complicated state psi, some psi let's call it. It made a black hole, okay, it's still some state psi prime. Then it made all these particle pairs and so on. The whole thing was described by some big quantum state, it's called psi double prime. Up to here everything is okay. But in the end, if this side is gone, and only these guys remain, they can't be described by any quantum state. And so you don't actually need to know what is the actual Hamiltonian for quantum gravity. Hawking said, I don't even care what the theory is or what the mechanics is. I know that black holes destroy quantum mechanics because in quantum mechanics you start with some state psi initial, at the end you have to get some other state psi final. But here you start with the psi initial, and now you end up with something which can't be described by any quantum state, and I have lost quantum mechanics. So this was Hawking's claim in 1975, and you can see it's a very simple and robust claim, and this is what is called the information paradox. So people didn't like this at all. Okay, Hawking was actually very happy. He said, black holes destroy information. I have a new discovery. But other people were not so happy because everybody knows and loves quantum mechanics, and they didn't want quantum mechanics to break down. So before we go to what they actually proposed, here I have another slide explaining why what is left doesn't actually have a quantum state. So here are two particles in a singlet. So I said spin up, down, minus, down, up, right? Two electrons, first particle and second particle. This particle I'll then make vanish from the world. Suppose this guy vanishes from the world, I'm left with this and this. You might say, okay, I can still give that a state, right? Almost looks like I should call this. So I just do this upside down. This should be down minus up. So you might think that if the total state is up, down, minus, down, up, if this guy vanishes, I'm left with down minus up. It almost looks like it has a quantum state. But it's not true. You can't do that. And the reason you can't do that, it's not down minus up, because in fact the same state could have been written in a different way. Right? I could actually say the up state is defined as up, and the other state, I've just got my arrows sort of backwards here, I'm sorry. If this guy was down, I could define e to the I theta times down as my down state. You could always give it a different phase, and I could put a phase e to the minus I theta on the other guy. Okay? And now if I make this particular particle vanish, then the state I would be left with is up and e to the minus I theta times down. So in fact, if you have two particles and you say, I will take one particle away, I want to see that the second guy has a definite state, you can't do that, because if you just change the basis, if you call the down ket vector as e to the I theta times the down ket vector and put a compensating phase in the other guy, and then take the first particle away, in one case you are left with this state, in the other case you are left with this state. As you know that this state, this minus this, is not the same as this state, this minus this. In fact, if you put theta equals pi, this becomes up plus down, this was up minus down, so this was an eigenstate of sigma x, and this was eigenstate of sigma y. They are completely different. So in fact, if you have two entangled electrons and you take one electron and you toss it out, the other electron can't be given any state at all. That's just a toy model to show why it can't be given a quantum state. Okay, so quantum mechanics broke down, and Hawking was actually happy with that. This is his quantum theory. You start with the complete initial state. You do that, you produce entangled pairs. I'll schematically write the entangled pairs in just 0, 0 plus 1, 1. It means there can be, occupation number 0, occupation number 0, or occupation number 1, occupation number 1. It doesn't matter how I write it schematically. The only thing is it's not something times something. This first guy corresponds to the in particle, second guy to the out particle. We typically just write it like this, say they are entangled with 0, 0 plus 1, 1, or 0, 0 plus 1, 1 plus 2, 2. You could make any set of states. This is a symbolic way of writing the fact that these two are entangled. And in the end, these guys went to a vacuum, and these guys had no states at all, and that conflicts with quantum theory. So that's the information paradox. And so because nobody liked this very much, people want to save their quantum mechanics. All the general relativity people came and said, no, when the black hole gets down to Planck size, the evaporation must stop. Yes?
So I'd like to just defend myself here.
Yes.
So the problem was not just that we like quantum mechanics.
Yes.
Therefore we have to save them. So depending on the specific mechanism by which quantum mechanics is violated, you could have random energy and momentum non-conservation in nature.
Yes.
And Lenny, Tom Bax, and I pointed this out in the paper.
Yes.
And,
by the virtual black hole fluctuations. Yes.
So I think that there are more serious problems than just that quantum mechanics is nice and people want to say.
Yes, so you're saying you could see things like local energy non-conservation if such things happened.
Absolutely.
Yes. So lots of bad things will happen, and I remember that as being a very interesting paper in this regard. So let's say you want to save quantum mechanics. Then one thing you could try to do is you could say the evaporation stops when you get to a Planck-sized remnant. We don't know why it should stop, because for that you would have to know something about quantum gravity. Okay? But now remnants are not so good either. It at least solves the problem for the moment. But now see what a difficult situation you've got yourself into. The remnant must have lots of internal states, because for every state outside, its mirror image was inside. So that inside the remnant, I should have this state, and this state, and this state, and this state, to the n states. How much is n? Now, n could be as big as I want, because I can start with a bigger and bigger black hole and evaporate down to a Planck-sized remnant. Start with an even bigger black hole and evaporate down to a Planck-sized remnant. So that will be bigger and bigger n. So in fact, the number of possible remnants I could make with all this stuff hiding in here is actually infinity. This is the same trouble we had come right in the beginning when we had said we have a big mass m, we put little masses, little m's in there and dial the whole energy down to, let's say, 0 or to Planck size, and we can make infinitely many remnants. So we'd already seen this trouble right in the first couple of slides, but now we have it a little bit more precisely. You have an infinite number of these remnants, and the question is, are we happy with that? Now normally this doesn't happen in physics. If you have an object which has size Planck length or some finite length and energy Planck energy or some finite energy, if you bound both the energy and momentum ranges, normally you have only a finite number of states, because one cell in phase space, delta x, delta p of the order of h bar, has one state in it. Okay, that's how you do quantization. But now in a bounded region with a bounded amount of energy, you're actually saying there should be infinitely many states. It's a little awkward, and a proper theory of a proper quantum theory will find this hard to do, because normally we can't put infinitely many states. The reason why you think you can do it here is because gravity itself is funny, right? You have a minus sign there, so it's a negative potential energy which is helping you. And I'll just come and talk a little bit about how people try to do this. I don't actually like any of those models. And you might think this is a little weird to put an infinite number of states inside that Planck region, but this is the best that the GR people can do. So if you go and talk to a typical GR person today who will perhaps doesn't like to do string theory, any of the things which come with string theory, in that case he would say, I do have remnants, all the information locked up in a Planck-sized thing. I can put infinite amount of information in a Planck-sized thing in there, and or he might just say, I believe that quantum mechanics is violated. Somebody like Bill Unruh would say, I don't want to preserve information. Somebody like Bob Wald would come and tell you, yes, I think there are remnants, and his picture for remnant is that it looks very small from outside, but in there with a narrow neck, you have a huge baby universe hiding in there. Okay, you could make a big baby universe in there, and then inside the baby universe, you could keep what you like. There are troubles with that. It turns out in general relativity, you can't actually make a space-time which comes like this, has a narrow neck, and then opens up to a baby universe. It looks like a very cute picture, right? You could have a space-time with a little hole somewhere in the middle of this room, and inside there could be hiding a huge amount of space where you could have a lot of people living there, okay? But the reason is that in general relativity, you have the Raychaudhuri equation, which tells you that if you have a beam of light, okay, it's just going like this, but if you put some mass there, it starts focusing. If you have positive mass, it focuses like this. If you had negative mass, it would defocus. But of course, there's no negative mass. As long as you assume that mass is always positive, It's called the null energy condition. If you use that, then everything just focuses. Nothing can defocus. But if you try to make something which comes in like this, narrows down, and then opens up, well, at first, the light rays coming this way will be focusing, but then you do need them to defocus because they have to go out if they follow the wormhole. And so you can actually prove, as long as you satisfy the null energy condition, a way of saying that mass is always positive, in that case, you can never actually create a wormhole. Okay. People still try to get around it by saying, well, that's a classical statement. You may get around it. The wormhole is very quantum, but it's a very ugly thing to do. Okay. And as we'll see that in string theory, you can't do that anyway. Okay. So remnants are another possible solution, and that doesn't look very good either. As I was saying, in string theory, you can't even have the remnants. And why is that? Because in string theory, if you believe in ADS-CFT duality, and I know not all of you might have been working with this, so you may not know what it is, so I'll just use it as a cartoon. I'm not going to use it for anything. What this says is that if you have, this is time going up again, and this is space as radial directions, the angular directions. If this space is anti-de Sitter space, then the boundary of this space, you can imagine a theory on the boundary, which is a normal conformal field theory, actually a Yang-Mills theory, and all the physics of the gravity that goes around inside this anti-de Sitter space can be read off in different variables as physics of this conformal field theory on the boundary. But if you look at the physics on the boundary, then in fact, you can only make a finitely many number of states for a finite energy. Okay? And if the physics on the boundary is exactly a description of what is happening inside in different variables, then inside in gravity, you can also only make finitely many states for a finite energy range. Okay? So in fact, if you have ADS-CFT duality, if you believe in that duality, you just cannot have something inside having remnants where for a given bounded mass, you have an infinite number of states. Okay? So this is the scales at which comes in this one, but it doesn't matter. We're just talking of whether you can have finitely many states or infinitely many, but this is the bottom line. If you have Planck-sized remnants in ADS, they will correspond to finitely many states in the CFT, and you cannot actually have remnants. Okay, so neither of our two solutions seem to be working. We had this black hole information paradox, and we had these puzzles. We can either stop the evaporation at Planck scale or let it evaporate completely. If it evaporates completely, we lose quantum mechanics, and certainly string theory wouldn't like that. So normal theory of quantum gravity, fully respecting quantum mechanics. And if you want to end at a remnant, well, at least you lose all things like ADS-CFT. Besides this fact, we actually know all the states at low energy in string theory. You just have strings and so on, just ordinary simple things. You have strings, you have brains. There's no magic which seems to be hiding at the Planck scale that we can find. Okay, so we basically know all the states are Planck energy. So we didn't really expect to find anything, and this argument really tells you you can't find anything. Okay, so again, let's put some questions down for ourselves, which you can ask somebody who has come to you with a theory of solving the information paradox. Does the entanglement keep rising as the pairs are produced? If not, why not? Okay, because the entanglement keeps rising, then you have the problem. At the end, when the black hole evaporates, what do you do with the entanglement, right? So if the entanglement doesn't keep rising, why not? Does the whole evaporate away completely? Or is there a remnant? If there's a remnant, do you have no analog of ADS-CFT duality? Okay, all the simple things we said, you can now summarize them as questions. Okay, given how much trouble we are having with the black hole, it might seem that you should just not have a horizon. If you could never actually put anything inside the horizon, like compress something to inside the horizon, then you would never have any place to put negative energy particles, and this whole thing would go away. Okay, so people did try to, we had seen that very low density stuff can make a horizon, but can we actually prevent it? Well, there are some results which tell you that this is not easy to do. So we've already seen if you have to make a horizon with a large radius r, you can do it with very low densities rho, and so it's very hard to stop the collapse. Well, can we quantify this hard business? So there's actually a beautiful theorem by Bugdal which says that suppose you take a ball of perfect fluid, okay, whose radius is less than 2 1/4 m. So remember r equals 2m. I have now put g equal to 1, c equal to 1, okay, just to make things clearer on the board. So if you take a radius which is less than 2 1/4 m, so bigger than the Schwarzschild radius 2m, then in fact this fluid star cannot be stable. It will actually keep collapsing. Okay, so once you have a star which is very big, of course, we know the sun is sitting out there, but once you make it even 2 1/4 m, it will actually collapse all the way down to 2m and then keep going in and just go to a point. So how did he prove this? Well, you take the metric and you write in the spherically symmetric ansatz. He assumes spherical symmetry. You take the stress tensor of perfect fluid, and you basically solve the hydrodynamic equations which say that the fluid is stabilized by the gradient of the pressure. So if you take any little cube of fluid here, it's being pulled in by the gravity that comes from the rho. But then also the pressure gradient P prime dP by dr, that's negative, and it's holding the guy out. Okay, so the pressure balance equation is P prime has something to do with P and rho. The attractive force also includes the relative situation. This is basically the pressure balance equation. Okay, at the surface of the object, you want the pressure to go to 0, and so you start with P equal to 0 here, and you start integrating this radially inwards. And then you find that if you started with a radius which was less than 2 1/4 m, 9/4 m, then by the time you come in up to some distance here, before you reach the center, the pressure blows off to infinity. If the pressure blows to infinity, you would say something bad has happened and the star must collapse, so I can't do this. So you can see it's even difficult to come close to 2m. If you're at let's say 2.1 m, you can't hold a ball of perfect fluid in there. Okay, of course you can say it doesn't have to be a perfect fluid and so on, but no, okay, this is an example of the kind of difficulty that you can get into. Okay, so this is what I said, the pressure actually goes to infinity at some point and the whole thing has to collapse. Okay, so again, if somebody gives you a theory, you can ask him if stars are allowed to reach a size less than 9/4 m, can collapse be prevented, and if so, how? Okay, so let me take just maybe a couple of minutes more and talk about this last topic and then stop. So if your horizon is not completely round and normal, the way we have been thinking, maybe something is wrong with the horizon. We can't stop the horizon from forming, but maybe Hawking took some simplistic view of the horizon, and there may be some structure around the horizon which can do something for us. It turns out you can't even do that. The fact you can't deform the horizon is what's called the no-hair theorem. Okay, but let's take a look at a little bit the no-hair theorems. So one theorem was by Bekenstein. If you take a metric of a black hole, you write out with a time form dt square with a coefficient which vanishes somewhere. That's the place where the horizon is. The coefficient vanishes at the place where you form a horizon. This is the space part just written in this form. And you take a normal scalar field here with a stable potential. Then in fact, if you try to add the scalar field to this metric, the only solution is phi equals constant, which has no energy because the gradient is 0. Okay, so how does this happen? What's basically happening is that if you take any geometry which has a horizon, and the horizon is the place where the coefficient of dt squared becomes 0, it wants to eat everything. Like we had seen from the picture, things are unstable, it just wants to eat everything. So if there was any scalar field hanging around outside the horizon, it just swallows it. So you can't get any time-independent solution where the field is like out there. Okay, phi equal to constant has no energy, so of course that can just stay there, but anything which really has any dynamics to phi, there's just no solution, and that's a very elegant proof that you simply can't have any phi hanging around the black hole. So the horizon can't be like dressed with having little scalar field around it. But this is actually a second point here, which has been a big source of confusion in the black hole game. People agree that you can't classically deform the horizon. It's round. If you want to deform it, then that's called adding hair, and you can't deform the horizon. It has to be round. But people say, look, classically, I don't want to change the horizon, but maybe quantum mechanical state around the horizon, I don't quite know. There might be some quantum mechanical hair which will be different from what you expect in a vacuum. Actually, it's very important that there is no quantum deformation possible either. Okay? And it's actually for the same reason there's no classical deformation, but you can't make a quantum deformation of the state either. And because this is a delicate point, let me take a little bit of time to just mention this, and then I'll stop. So take a black hole with a normal horizon, and take a scalar field satisfying the equation box phi equal to 0. Its solutions look like this. Okay? And okay, so that's a massless scalar field, and that's how you solve it. How do you do quantum field theory? In quantum field theory, you take the solutions of the massless field equation, you take their complex conjugates, they should have a minus I here, and then you put annihilation operators here and creation operators here, and that's your quantum field, and then you put these commutation relations. This is just basic quantum field theory. I'm just reminding you of that. And so each mode behaves like a harmonic oscillator, and the vacuum, I'm not talking about flat space, is a state which is killed by all the annihilation operators. I'm just writing down the standard formulation of what we do in flat space to get the flat space vacuum. Then how do you get the other states which are not the vacuum? If you want to create some particles, you act with the creation operators, and then you have a one particle state with one A dagger, n particle state if you have nk daggers. If you make a coherent state, you put e to the some number times the A dagger, that makes a coherent state, and that's the analog of classical modifications. So actually there's not much difference between the classical problem and the quantum problem. If the classical problem had a solution of box phi equal to 0 in terms of some Fourier modes, then in that case the quantum problem, you take the same Fourier modes, and you add them to these AKs and AK daggers, and then you actually excite particles by using the same quantum modes. Okay. So actually, if there are no solutions to the classical problem, which can create any hair, we'll see in a minute you actually can't create any quantum hair either. They're actually coming from the same source, because the same solution of the wave equation go into the quantum field as solve the wave equation in classical physics. Okay, so this is how you actually make states in quantum theory. And so now let's go and see what you would do in a case with general relativity. But first let's look at the case where you have just a star. Okay. So if you take a star, then okay, Now you start to solve box phi equal to 0, but there's some metric there which is not equal to eta AB. Okay, you go ahead and solve it, and let the solutions be equal to Fi of x. Again, you take Fi of x here, multiply with annihilation operators, take the complex conjugates, multiply with creation operators, you define the quantum field. I'm just doing this around a star. So the star is in some ground state, where if I act with all the annihilation operators equal to 0, I can say around the star, the quantum field phi is in the ground state. Does that make sense? I have a star here, I have no particles of the phi field, only the star. Okay, so the phi field, you would quantize it this way, and you see there are no particles, and if I want to put some particles around the star, I put creation operators. Okay, so of course you can do quantum field theory around the star. And so if you want to add the hair around the star, I just did it more explicitly. You have these functions f would have a radial part, a y lm part. We don't actually care about the details, but the vacuum is annihilated by all the a's. And if you act with creation operators, you would be adding here. If you act with exponentials of creation operators, you get classical deformations. Okay, so the classical deformation, the quantum deformation are really part of the same story. You have to solve the same wave equation, box phi equal to 0. If you add them as coefficients of the A daggers, you change the quantum state. If you add them like this, you end up changing for the same classical wave equations. You end up making a classical deformation. But now if you have a horizon and not a star, you try to solve box phi equal to 0, you try to write ylm of theta phi times function of r, e to the minus I omega t, the same way you're trying to make the modes. The coefficient of each of these functions like this would be the A and the A dagger, and you think you can do it as before. You can add the A daggers and create particles and like change the quantum state around the vacuum. But now it doesn't work. You try to solve the equation for this f of r, and you find this equation is singular. It's the same reason so that's why you actually cannot solve the classical equation. Otherwise you could have solved the same classical equation and got some here. But if you can't solve the classical wave equation, you can't find the modes f which go into the quantum field expansion either. So there are no stationary solutions which you could actually add to the quantum theory. And the reason you can't actually get any good solutions to the f of r is basically what you already know from classical physics. The wave function starts oscillating infinitely rapidly as you go in here, and just because there's infinite blue shift, which is the same as saying that any particle just wants to get sucked in. As because everything wants to get sucked in, there's no time-independent solutions like this. If there are no time-independent solutions like this, classically you won't have a field hanging around the horizon. Quantum mechanically you can't actually get the fields which multiply A and A dagger, and so you quantize the field and try to say, I can change the vacuum, but in fact you can't. So there's no way to actually set up a different quantum state around the horizon, and so in fact you always get just the horizon, and the state around here is the actual normal quantum vacuum, just like this room. That's going to be very important for us, because when we see the Hawking pair production process a little bit more detail, it's actually a quantum process. We were just doing little hand-waving things, a particle, antiparticle comes out and all. But really, if you want to do that properly, you're looking at evolution of quantum field theory modes. And you won't know what state you're starting in, because you're going to evolve to quantum field in a certain way. But the vacuum around the horizon is just going to be the same as the vacuum in this room. You can't delicately hide some new information in the vacuum and make it a different vacuum. So in fact, you can't change the structure here at all, and so you can't make the horizon something different, and so in fact, you have your problem. And so if anybody comes to you with a theory of the black hole, you have to ask him, is there hair of any kind at the horizon? If so, how? People have shown you can't get classical hair, and if you can't get classical hair, you can't change the quantum state either. They're really the same problem. And so is the state around the horizon the normal vacuum? And if so, why don't you have a problem? I'll stop here for the first part, and we'll continue after the break.